So we last left off at the previous video. We had just written the general form of the solution for example 2, and this is what we have. And what you notice is that we have two free variables and one basic variable. Now, I had at the tail end of that video, I had asked you if the point, and let me make sure I recall, I think the point was 23, 10, 100. I had simply asked the question, is 23, 10, 100, is that a solution to this system? So if you were to plug 23 in, well, really quickly, let's just go ahead and do that. So 10 multiplied by 23 minus 3 multiplied by 10 minus 2 multiplied by 100, does that equal 0? And the answer is yes. If you were to multiply that out, you indeed get 230, and then negative 30, negative 200. So 230 minus 230 is 0. 0 equals 0. So yes. So yes, that is a solution. Now, how did I just randomly get this point 23, 10, 100? Well, remember that your free variables are x sub 2 and x sub 3. So when I generated that point, truthfully, I just chose some random number for x sub 2. I just said 10. And then I chose some random number for x sub 3. I just said 100. These were arbitrary. But what comes next is not. So now that I have defined x sub 2, I need to make sure I plug it in here. And now that I've defined x sub 3, I need to plug it in here. And when I did, that's when I got x sub 1 is equal to 23. Okay? So that is one of the infinite amount of solutions. Now, let me see if I can do this next question justice, because this is very important part, right? All right. So describe, remember, you have matrix A times vector x must equal 0. And we want to describe vector x, right? The solution. We want to describe vector x as a linear combination of two vectors. So vector x, well, first off, let's establish that, let's look at the variables. The variables are x sub 1, x sub 2, x sub 3. So vector x can be described as the following column vector. That's really what it means, right? Vector x is this column vector. And now, notice that we want to, since we're trying to write it as a linear combination of two other vectors, we need to figure out what the other two vectors are. And this is the way we're going to do this. So notice that x sub 1 is equal to the following: 0.3 x sub 2 plus 2.2 x sub 3. So I'm going to insert that for x sub 1 right here. So 0.3 x sub 2 plus 0.2 x sub 3. Okay, so that has been inserted for x sub 1. Now, what do I place here for x sub 2? What do I place here for x sub 3? Well, since it's free, that means you get to choose whatever you want, right? So if you choose 10, then x sub 2 is equal to 10. So x sub 2 is just simply equal to itself, right? Does that make sense? X sub 2 is always equal to whatever you choose. So x sub 2 is just equal to x sub 2. And x sub 3 is equal to, again, itself. Notice that it's the basic variable. I'll say it really slow. There's no other way to describe your free variables than itself. But notice the basic variable you can describe using free variables. All right, in terms of free variables. Ready? So now you will probably get faster at this, and you might be able to jump a couple of these steps. But for now, just so you have good notes, what I'm going to do is I'm going to break this matrix up. Right? I'm going to break this matrix up into, since there's two free variables, I want to break it up into two vectors. Now I want any x sub 2's to go here, and I want x sub 3's to go here. So I want all the x sub 2's to go here. I want all the x sub 3's to go here. So let's go ahead and break that up. So we're going to have 0.3 x sub 2. That's going to go in the x sub 2 vector. So 0.3 x sub 2. All right, well, x sub 2 is also going to go in the x sub 2 vector. And now when we go to the third row, well, are there any x sub 2's here? No, there's none. So for our third row, we got to have 0 x sub 2's. Let's do the same thing for x sub 3. So the first row has 0.2 x sub 3. So 0.2 x sub 3. The second row, how many x sub 3's are in the second row? None, right? There are no x sub 3's in the second row. How many x sub 3? Well, so there is an x sub 3 in the third row. Okay. So now and henceforth, you can jump. You can skip this step and you can jump right to this step. Assuming that you see it, right? I think this step sometimes can keep your work neat enough to where you don't make any silly mistakes. But now what we're going to do is we're going to factor out an x sub 2. All right, so I'm going to factor an x sub 2 out of that first vector. And let's figure out what's left. So if I factor an x sub 2 out of this first row, you with me that all I have is a 0.3 left? If I factor an x sub 2 out of the second row, all I have is a 1. Right? If you factor an x sub 2 from an x sub 2, you have 1 left. And then, of course, if you can't factor an x sub 2 if you don't have any. So there's 0. All right, plus. And now we're going to do the same thing. We're going to factor an x sub 3 out of this second vector. So factoring out an x sub 3, I would have 0.2 left here. If you don't have any x sub 3's, you can't factor any out. And if I have 1 x sub 3, but I factor it out, I have 1 left. Right? So if you factor an x sub 3 from an x sub 3, you just have 1. Now, here it is. So I'm going to give you a second. I'm going to give you a second to understand what it is that you've just done. More importantly, I guess I could say, to understand what are you trying to do. You're trying to write a vector x as a linear combination, right? Again, if this language is messing with you, I can't help you. You remember a linear combination, that's back to that, say, c sub 1 times v plus c sub 2 times u. You got to be able to grab that information from the lecture. Well, here it is. So what we have is this vector is what we can call v, 0.310, right? Again, my engineers, that's your I, your J, your K. This is going to be some other vector. I'll just call it u, I guess. So plus x sub 3u. And again, your I, J, K. And here it is. So we are done with this problem. But if I were to graph, right, just think about it. If you were to go 0.3, if you go 0.3 in the I direction, 1 in the J direction, but 0 in the K direction, this is vector V. Then if you go 0.2, 0, 1, this is vector U. Vector V, vector U. Okay. Now, do you see all of this, all of these points that can be generated from these two vectors? Guess what? One of those points is the 23, 10, 100. That's in here. So is 0, 0, 0. That's in here too. What you're looking at geometrically, this is the span of these vectors. And I hope it makes sense. I do hope it makes sense that this point, 23, 10, 100, is in the span of these two vectors. And what that simply means, and then we'll be done with this problem. If you put a 10 here and a 100 here, you will build 23, 10, 100. And if you do, I won't go any further than that. I hope that all of this terminology is starting to come together. I do want to knock out example 3, but we'll go quickly. It's because I've already laid all the foundation. Before I do that, let's say I were to give you the following system, and right here, see if you've been paying attention to me. The question is, how can you tell that the following system does have non-trivial solutions, right? Something other than 0, 0, 0. How can you tell this system has non-trivial solutions, here it is, without solving it? Right? How could you do it without solving? Well, let's make sure you understand. If there is a non-trivial solution, there must be a free variable. Do you agree with me? How many equations? I got 2 equations. How many variables? 3 variables. Do I have more variables than equations? I do. I have 3 variables, but only 2 equations. I have more variables than equations, so I must have free variables. Must have at least one free variable. And if I have one free variable, then I have more than just 0, 0, 0 as a solution. Okay. So example 3, notice that this is not an homogeneous equation, right? This is a non-homogeneous equation. So just, again, keeping our language under control here. So it's non-homogeneous because it's not set equal to 0, right? Right, when we had 0, 0, 0 here, then we had a homogeneous equation. But look at B. B is not a 0, 0, 0. So, all right, so what do we do with non-homogeneous systems? How do we solve them? Well, notice it says describe all the solutions. AX equals B. So here's A, 3 by 3 matrix, and here's B. What are you doing? Right? I mean, we're doing stuff, but what are we doing? All I'm simply asking you is what vectors, listen to me, what vectors are out there that when you multiply matrix A by that vector, it will get you to this vector B? How many ways is there to get to this vector B? Or can you get to vector B? Maybe you can't. Well, that's what I'm trying to figure out. And the good news is, if you haven't guessed it, yes, we are going to indeed form an augmented matrix. This becomes our columns, and this is that last column. It is quite beautiful how effective matrices are. I'll be honest with you while I'm writing this, that I would, if I had to bet, I would venture to say, and I have done consulting work before. I would venture to say that 90% of all applied mathematics, meaning math someone in the private sector is going to pay you to do, right? Or public sector, but 90% of all applied mathematics, I would assume, ends up coming down to a system of equations in the end. Anyway, that's just a guess. Okay, so this is my augmented matrix, and you know where we go from here. We row reduce, echelon form. This is what your calculator should be telling you. Okay, and remember, the goal is to describe all the solutions, so we want to get to the general form. So at this stage, I will go back to system, and then I will get to general form. So let's get back out of matrix, back to system form. So x sub 1 minus 4/3 x sub 3 equals -1. Here we have x sub 2 is equal to 2. And that last row, meaning last equation, is just 0 equals 0. Okay, again, optional step. The goal is to get to this next step. So, do we have any free variables? Well, I have a pivot here. That's a basic variable. Pivot here, that's a basic variable. No pivot here. So x sub 3 is free. So yes, there are free variables. This is the free variable. So let's go ahead and solve for our basic variables. So get x sub 1 by itself. So that's going to be, so x sub 1 is equal to, x sub 2 is equal to, x sub 3 is, of course, free. All right, ready? So x sub 1 is equal to -1 plus 4/3 x sub 3. And x sub 2 is, well, x sub 2 is just equal to 2. There it is. There is your general form that describes all the solutions to that ax equals b. I hope that makes sense. The only, like, this is just kind of a snapshot of example 1 and example 3. See how they're very similar, the solutions are. Only that example 3, you can, let me see if I can try to explain it this way. Do you remember you had vertical translations, right? Where if I have, let's say this is, so here's the graph, let's assume of f of x equals x squared. Now, if I had f of x equals x squared plus 1, it makes sense to you that just takes x squared and just shifts it up 1 unit, doesn't it? Right? It's a vertical translation. We just go up 1 unit. All the y values increase by 1 unit. Well, what I'm trying to tell you is with these non-homogeneous equations, they too can be thought of in terms of vertical translations. But at this stage, I will go ahead and just leave you with these pictures that you can take a look at the geometry of. But we are done with 1.5.